So we're in section 10.2. We're going to finish that up. It might not take the full time. There are kind of a few scraps left. One of those scraps is telescoping series. These are not things you see very often in real world situations, so I don't want to dwell on them. But suppose you have something like this. We're going from 1 to infinity here, and you want to know, does this series converge? And if it converges, what does it converge to? That second question is often not a realistic one, but I mean, the only thing we know at this point is that we can look at partial sums. But we also see that, partial sums, what is this? 1/2 plus 1/6. Partial sums do not provide a great, I hope it's not going to spend the rest of the class doing that. Partial sums do not provide a great way of answering these questions most of the time. What are these partial sums going to? It's totally unclear. And that's the standard. That's the usual situation. So what we're going to talk about now is very much an exception. But in this particular case, you can use partial sums to investigate convergence or divergence if you happen to recognize that 1/n times n plus 1 can be decomposed like that. This is a partial fraction decomposition. I'm not doing the details on the board, but partial fraction decomposition says that if we have the denominator factored like that, we can write it as that sum, and the denominator is factored like that. And when we write it as this sum, this is what we get. And it might not seem like that's an improvement. Does anybody mind the window open? I can't deal well with the heat, but okay, thank you. So the first partial sum, remember, I mean, I've been just kind of doing this. These partial sums are what you get if you replace that upper bound with, well, in this case, with 1. So it's 1/1 minus 1/2. The second partial sum one over one minus 1/2 plus 1/2 minus 1/3. The third partial sum is 1/1 minus 1/2 plus 1/2 minus 1/3. Really is just gonna, we're probably not seeing this in the recording. If you're watching the recording, the screen keeps going black on me. Anyway, the third partial sum is equal to this. The fourth partial sum is this. If we now pause and take stock of these partial sums, all of them have significant cancellation. -1/2 plus 1/2. -1/2 plus 1/2, -1/3 plus 1/3. -1/2 plus 1/2, -1/3 plus 1/3, negative and positive 1/4. All of the middle terms in all of these partial sums are, if I had the least idea how to fix this, I would pause class and fix this. I'm sure it's easy, but all of the middle terms are canceling and we're being left with the first terms and the last terms. And the first term is always 1. And if you look at the last term, 1/2, 1/3, 1/4, 1/5. That's a pretty predictable pattern. The next one is going to be 1/6. S sub n is 1 minus 1 over n plus 1. And if you're taking the limit as n goes to infinity, we get 1. So again, this is a pretty flukish situation, but we were able not only to verify that this thing converges, we were able to find what it converges to. And when this happens, it's a telescoping series. I don't know if they have them. I feel like it was pretty quaint in my day, but like a plastic or a metal telescope that collapses in for storage. That's the reason here. The idea that we have this lengthy telescope, but it collapses and we're only left with the eyepiece and the lens, the first and the last piece. Otherwise, we have theorems in this section, and these theorems are going to be useful. Sometimes it feels like calculus textbooks do just present theorems and we never use them for anything. That's not going to be the case here. So the first theorem, in all of these examples I've done, we've had sums from 1 to infinity. This first result says the sum from 1 to infinity converges if and only if the sum from any number capital N to infinity converges. And the same is true for divergence. Saying that this is useful, let's look ahead a bit. We're going to learn a series of tests for determining whether series converge or diverge. And a lot of those tests have restrictions on them. The most common restriction is that all of the terms have to be positive. There are other possible restrictions as well. Suppose you have something like, just sort of making something up. But suppose you have a series that looks like this, and you want to determine whether this series converges or diverges. Well, we have tests that will allow us to determine that this series diverges. Again, looking ahead a bit. But the tests that we're going to use requires that all the terms be positive. So actually, we can't use it. And we say, well, according to the theorem, you know, if we're interested in this series, here are our, zero isn't a problem, but we'll include it. Here are our problem terms. And this theorem says that, well, if we just get rid of the first three terms and start with the fourth term, then if that series diverges, the original series also diverges. So this theorem is useful when we've got a few terms that are causing problems and we want to just get rid of them. We'll see this tomorrow as well. There's a test we have, and to use the test, these entries have to always be decreasing, which in this particular example, they are. But suppose we have something that, again, this is a pretty artificial example, but suppose we have a series that looks like this. And we want to hit it with a convergence test. But the convergence test we want to use says that from left to right, these terms need to decrease, otherwise we can't use the test. Well, they're not. 2 is bigger than 1, 3 is bigger than 2. But according to this theorem, we can just ignore the first few terms and start with the 1/2. And we can now hit this with our test, and we can see that it diverges, so we can see that the original series diverges. So this gets used to sort of massage series when they almost satisfy the conditions of a test, but there are a few terms that are messing things up. This next series, or this next theorem, I should say, is not so useful in itself, but it has a few important corollaries. And it says, well, suppose we have two convergent series. And this bit of, I guess you could call it sloppiness, but it's extremely common when we're writing series down, not to bother with the little subscript and the superscript. And that's just because, well, we're working with infinite series. The number up here is always going to be infinity. And we've just seen that as far as convergence and divergence, the number down there doesn't matter. So we often just write what you see here, the capital sigma. If these two series converge, and they converge specifically to numbers that we know, to A and to B, then this series created by addition or subtraction also converges to A and to B. And I mean, this is a fact about finite addition, right? For finite addition, if you have 1 plus 2 plus 3, I feel like it's getting worse every time. I mean, if you have two finite sums and you're adding them together, we can change the order so that we've got 1 plus 4 and 2 plus 6 and 3 plus 7. And that's all we're doing. It's just in an infinite case. And I say just, this is significant because we can't always treat infinite sums like finite sums. We saw that with Grandy's series. Grandy's series was the one where if we put parentheses in, we can change what it adds up to. That's not true with finite sums. With finite sums, we can put parentheses in wherever we want. So the fact that this infinite sum acts like a finite sum is not obvious. It's something that has to be said. Similarly, if this sum converges to A, and if we put a K there, it converges to K times A. And this is the statement that multiplication distributes over addition applied to infinite series. You know, 2 times 3 plus 2 times 4 plus 2 times 5 is 2 times 3 plus 4 thus 5. That's a true fact about finite sums. It's also true of these convergent infinite sums, of these infinite series. And what we really want from this theorem, again, it's not realistic to expect that we usually know these precise sums. But this tells us that if some series converges, so does a constant times that series. And similarly, if a series diverges, so does a constant times the series. I guess that second statement needs the footnote that, of course, that k can't be 0, but that's obvious, maybe. And I mean, we use this theorem all the time. I've mentioned this a few times now. We're going to see tomorrow that series 1 over n diverges. I've mentioned it a few times now. Now, what if we don't have 1 over n? What if we have 5 over n or 2 over n? Well, 5 over n, that's a constant multiple of 1 over n, and 1 over n diverges. So, according to this theorem, 5 over n also diverges. You need to be, addition and subtraction is delicate. So we have this result. If we have two convergent series and we add them or subtract them, the result is convergent. What about divergent series? Or what if we have a convergent series and a divergent series? Well, we have partial results. Suppose one series converges and another series diverges. Know why I wrote that? Then this diverges. And it might help to think that most divergent series we look at in day-to-day mathematics are diverging because the sum is getting infinitely big. It's going to infinity. I mean, that's sort of the default state, right? If we add infinite things together, we get infinity. It's quite rare that we don't. So, I mean, if we think of it in those terms, it makes perfect sense. We've got a finite thing plus an infinite thing, the result is still infinite. We've got a finite thing minus an infinite thing, the result is still infinite, or negative infinite. But we need to be careful with the results we don't have. If A sub n diverges and B sub n diverges, just as well that I didn't have a very long lesson planned. We have no information about A sub n plus or minus B sub n. And that might seem unintuitive because surely if these are both going to infinity, then their sum is going to infinity. But I mean, the easiest example is that both these series diverge. I mean, 1 plus 1 is 1, is 2, 1 plus 1 plus 1 is 3, 1 plus 1 plus 1 plus 1 is 4. These partial sums are going to infinity. These partial sums are going to negative infinity. These both diverge, and, well, if we add these divergent series together, we get the convergent series. We get 0. So because infinite sums can cancel each other out, as it were, the fact that individual pieces diverge doesn't tell us anything about the sum. And that's that. We'll go one section ahead of what's on Canvas. We'll do the integral test tomorrow. I hope that whatever's going on with this whiteboard is just a phase it's going through. I mean, we've already had to loot one of the boards from the circumference of the room. We can do it again if we have to, I guess, but I hope it doesn't come to that. And